Okay. So we're thinking about what we're going to refer to as elementary reactions. So an elementary reaction is a reaction that occurs in a single step. Okay, we can show that it's going to occur in a single step. It is a very simple reaction. Okay, it is going to be each of the lines of the reaction mechanism. There is one very nice thing that we can do with an elementary reaction, and that is we can determine the rate law for a reaction based on if it's an elementary reaction without having to do too much work. So I'm just going to write for now, for elementary reactions, we can easily determine the rate law. We'll do an example here in a little bit, and I'll show you how easily that actually is. So the number of molecules that are needed to make a reaction happen is what we refer to as the molecularity of that reaction. So if we have one molecule involved in that reaction, it's a unimolecular reaction. So if we have, for instance, we'll use some spheres. Here's one molecule, and it decomposes into two things. That is a unimolecular reaction. If we have a reaction that involves two molecules colliding, that is a bimolecular reaction. Those are ones we most, well, the unimolecular and bimolecular are the ones we see the most commonly. A termolecular reaction is possible, but it is highly improbable because for a termolecular process to happen, we would have to have three molecules collide all at once, and that's very unlikely. There is one example, and I can't remember if it's in your textbook, but we use, it involves different gases, and they react together and happen to collide three at once. It's kind of interesting. But again, not very common. So we're really not going to see too many of those. So each of these diagrams on the right-hand side of the slide are representing bimolecular reactions. So we have two molecules colliding to form two other molecules. We can have two molecules or a molecule and an atom colliding to form one species. Okay, those are both bimolecular reactions. We're looking at what is happening on the reaction side. Okay, so I mentioned our reaction coordinate diagrams were going to get a little bit more complicated. And that's what we have here. All right, so we have a reaction coordinate diagram, just like before, reaction progress going from reactants to products on the x-axis, and potential energy on our y-axis. Okay? In this example, you'll notice that we have two hills. Okay? And what our two hills are representing are two different steps in a reaction. From our reactant, we will climb the first hill, go over the transition state. Remember, we have that activated complex at the top of the hill. And we go and form an intermediate. An intermediate is a species that we don't actually write in our balanced chemical equation. Okay? So we wouldn't know that it was there, and sometimes in reality we don't actually know that they're there until we do more experiments. But from that intermediate, we're going to go up another hill, another activation energy, and get to the products. And we'll have another transition state. So an intermediate is formed in one elementary step and consumed in another. Okay? We don't see them in the balanced overall equation. So let's look at some really generic examples. We're going to use A and B to represent two molecules that are going to collide and form another molecule, AB. Okay? So step one for the reaction, whoops. We're going to have A plus B reacts to form AB. Step two in the reaction, we're going to have AB plus another B form BAB. Do you remember combining chemical equations? And I think you probably did this in Hess's law. If we combine these two steps, we cancel out AB, and what we're left with on the reactant side is A plus 2B, and we form BAB. Okay? So when we combine these reactions, the thing that we cancel out is when it occurs on the product side and then the reactant side, that's going to be an intermediate. Okay? So we can identify where, or we can add our reactants, products, and intermediates to our reaction progress diagram. Okay? And we only use, well, this is sort of half true. For adding things, we're going to mostly be looking at the overall reaction. That's where we're going to identify our reactants and our products. But we're going to also add an intermediate, and that's the thing that we canceled out. Okay. So our reactants are going to be A plus 2B. And our product is going to be BAB. Okay, notice I didn't include AB as the reactant. That is an intermediate. It's created in step one and used up in step two. Okay? Now the transition states or the activated complex, we wouldn't ask you to identify those. Truly experimentally, they are incredibly difficult to identify. So we would just be making things up if we did that. Okay? Questions on identifying reactants, products, intermediates? Okay. All right, so I'm going to have you take a couple minutes, look at these two elementary reactions, step one and step two. I want you to write the overall reaction, determine the molecularity of each reaction, each elementary reaction, and then we'll recombine and write the rate law together, and you can also identify intermediates, okay? So take a couple minutes, feel free to talk to your neighbors. Do that. Okay. So in order to write our overall reaction, I'm going to look at my reactants and my products and determine if there are intermediates, and if there are intermediates, I'm going to kind of cancel them out and then add everything up. So in my reaction, I have H2 plus ICl forming HI and HCl in step 1. Then I have HI and ICl forming I2 and HCl. So I have HI formed as a product in step 1 and used up as a reactant in step 2. So I'm going to cancel those. And immediately I know that that is going to be an intermediate. Okay. Writing the overall reaction, just going to combine the rest of the reactants and the rest of the products. So I'll have H2 plus 2 ICl forming I2 plus 2 HCl. It's a good idea at this point to make sure that the reaction is balanced. So we can add up the number of H2 on both sides, number of I2 on both sides, and Cl on both sides. And I think we are looking pretty good. Cool. Questions on that? Pretty straightforward, hopefully. Okay, so then what is the molecularity of each of these reactions? We got peace signs happening, which is good. So we've got some bimolecular, 2 bimolecular reactions. Both step 1 and step 2 are bimolecular. Okay. So I told you that writing the rate law for elementary reactions is really easy. I meant that. Okay, we don't have to go through a bunch of steps like we've done in our previous sections. This is the only time when writing rate laws is actually easy. Okay, so in this case, the rate law for step 1, we're going to have rate equals K times the reactants. So for step 1, it's rate equals K times H2 times ICl. Yeah?
Will they ever be raised in coordinates?
So often the answer is no, and I'm actually anticipating that question and trying to think of if it is possible. It is possible to have so you could have, if we had 2 HI colliding, we would have HI squared in that case. That could still be an elementary reaction. So you can't have it raised to a power, but it often isn't. It's just by way of writing an elementary reaction, we're kind of limiting ourselves by the number of things that can collide and the orders in which they sort of play out. So then for step 2, rate equals rate constant K times HI times ICl. And I did include the intermediate in this rate law. Okay? That is the rate law for the elementary reaction. It's not the rate law for the overall reaction. And that's going to be one additional step that we're going to see here in a minute. Okay? So only in the case of writing a rate law for an elementary reaction can you possibly have an intermediate show up. Questions on that? We won't often ask you to write rate laws for elementary reactions. Okay. So if we were to look at the same reaction, our reaction coordinate diagram, here we have H2 and ICl. We have a transition state. We get to a reaction intermediate, another transition state, and on to products. Okay? So just sort of reiterating the fact that we will have reaction coordinate diagrams of mechanisms, and they can end up being very complicated. So is there a way to know if our proposed mechanism, our step 1 or step 2, however many steps, is that correct? There is not a way to prove that it is correct. All right? There is a way to disprove it. We can very easily disprove a reaction mechanism, but it is much harder to prove that it is correct. Okay? What we can do, though, is we can say that the mechanism is consistent with experimental data. Okay? So we are going to look now at 2 different types of mechanisms. The first type where we have a slow initial step. The second type where we have a fast and reversible first step, and then a slow second step. Okay. We're going to write rate laws. Relate this to rate. So we're going to write rate laws for each of these types of reaction mechanisms. Okay. For mechanisms with a slow initial step, okay, we write the rate law based on that slow that slow elementary reaction. So let me write this down. For mechanisms with the slow initial step, the rate law is predicted from the slow step. Okay. And just to reiterate what we've been thinking about, a slow initial step, that's the one that's going to have the biggest activation energy, okay, the tallest hill. Any steps past that, second step, if there's a third step, they're going to have much smaller activation energies. Okay. So using these 2 elementary reactions, these are representing this overall reaction where we have NO2 plus CO forming NO and CO2. A proposed mechanism for this is that we have NO2 plus NO2 forming NO3 and NO, and then step 2 having NO3 plus CO forming NO2 and CO2. Okay. What could be told is that the experimentally determined or experimentally derived rate law here is rate equals K times the concentration of NO2 squared. If we write our rate law based on the slow step, because it's an elementary reaction, we'll have rate equals K times NO2 squared. It's NO2 times NO2. Everyone see that? Okay. And so yes, that rate law is consistent with the experimentally determined one. Okay. Just to sort of, again, reiterate what we're doing here with our steps in the rate law. Okay. If we add these up, we have NO3 produced in the first step. It's consumed immediately in the second step. And we actually have an NO produced here and one used here. So we're going to cancel those out. That's where this is going to allow us to get to this overall reaction. So we'll have, if we sum these up, NO2 plus CO forms NO plus CO2, leaving off all my gas phases there. Yeah?
How do we know that the energy is second order if it doesn't depend on coefficients? I thought like since there's 2 NO2s, I felt like it's not.
Oh, mathematically it's the same. Yeah. So, yes, from the proposed mechanism, we could write K times NO2 times NO2. Is that what you mean?
I mean, like, since it's 2 and O2, I thought that the coefficients like were not allowed to. Never mind.
Okay. Cool. We can talk later. Yes.
I like also have a question can you use coefficients to determine the NN for the rate law? Because I thought you weren't allowed to, but in this case you are using.
Great. So the question is, can you use the coefficients to determine N and N? Oh, yes, only if it's an elementary reaction. That's where it is. Thank you. Okay, now we get it. And you'll know it's an elementary reaction if we say, hey, this is a mechanism. We didn't explicitly say in this problem, these are elementary reactions. But if you're given step 1, step 2, step 3, and it's like, hey, this is the overall mechanism, you know these are elementary. Cool. Yes. So going back, thinking back to what we've done in the last week and a half or whatever it's been, if we didn't know it was an elementary reaction, we cannot use the stoichiometry to get the rate law. Okay. That's a special thing for elementary reactions. Cool. Other questions? All right, so you take your turn, write out the chemical equation for these two steps. These are two elementary reactions in this mechanism. Write out the chemical equation for the overall process, and then predict what the rate law for the overall process would be, for the overall process. Okay. There's the first step is slow, and the second step is fast. Okay. All right, so writing the overall chemical process, we're going to cancel out species that occur on the reactant side in one reaction and the product side of another, or vice versa. Okay, so we have IO that shows up in the IO minus that shows up in the product side of this first slow step, and then in the reactant side. Okay. We also have this I minus. I'm going to circle this one. It shows up in the reactant side on the first step, and then the product side in the second step. We're not going to include that because technically those cancel out. So for the overall process, we have H2O2 plus H2O2. So we're going to have two H2O2s form 2H2O plus O2. Again, being sloppy and leaving off all my phases. Okay, everyone okay with that? All right. So I minus is kind of special. That's why I've circled it. Okay. It shows up in the reactant side of the first step and the product side of the second step. So basically what it's saying is that we use it and then it's reproduced. And what that really is it's a catalyst. We're going to talk more about catalysts here in a couple slides. But a catalyst allows a reaction to go faster than it would without it. And speeds the process. It increases the rate, and what it really does is it lowers the activation energy for a reaction. IO minus is an intermediate. It's formed as the product first, and then it's consumed as the reactant in the second step. Right? So there's a slight difference there. Right? It doesn't show up on the product side at the end. That's an intermediate. So what did we get for our overall rate? 1, 2, 3, or 4? Some ones. So this is based on the slow elementary step. Excuse me. So that is this first reaction. And so if we write the rate law based on that, we'll have rate equals K times the concentration of H2O2 times the concentration of I minus. And the catalyst can show up in the rate law. An intermediate cannot. We'll get to that. But a catalyst can. Okay. Questions on that? Okay. This next slide shows a proposed energy progress diagram. Reactants, big first activation energy, forming an intermediate, and then going to products. Okay? And so what this is going to show us is that the activation energy going from the reactant in step 1 to any intermediates, the activation is bigger. If we go from the intermediates, the activation is much smaller, activation energy. And so when we have a large activation energy, that means that the rate is slow. So this sort of diagram would be consistent with a slow initial step and a fast second step. Okay, so let's say we have a reaction 2A plus B forms C plus D. And we say that the rate law is rate equals K times B. Which of these options, option A or option B, is consistent with this rate law? Take a look at those. So in both of these, we have a slow first step, okay, which means that we could get the rate law based on that first elementary reaction. So for option A, we would get rate equals K times the concentration of A times the concentration of B. And in option B, we would have rate equals K times the concentration of B. So even though there's a bunch of other stuff following both of those first steps, it doesn't really matter. We could have written several hundred other lines. But because that first step is the slow one, that's what is setting the rate law. Okay? That's the one that's making it so the reaction only goes at a certain speed. Okay? And so as we've written with the slow first step, rate law is equal to the concentration of the reactants in that slow elementary step. And so option B would be consistent with rate equals K times B, right? Does that make sense? Okay, so sort of at least mathematically more interesting. We have we could have a fast first step, and it's usually reversible. It will always be reversible. And then a slow second step. Okay. These we can't just write the rate law based on the second step, or the slow step. Okay. And if we look at this first one, this first example, we've got an intermediate. So M is an intermediate, and we can't have intermediates in the rate law. So even if we tried to write rate equals K times, in this case, B times M based on that slow step, M is an intermediate, that won't work for the rate law. So we need another plan. What our plan is going to be is to write an equation that will substitute for M. We need an equation to substitute for M. And technically M in brackets. Okay. The other thing I want to draw your attention to is this. Okay. Those are equilibrium arrows. Right? So our equilibrium arrows are going to signify the fact that the forward reaction of that A plus A equals M, forward reaction is happening, and the reverse reaction is happening. So M is decomposing into A plus A. And they are in equilibrium. Okay? That's great. That is good for us, because what that means is that the forward rate is equal to the reverse rate. So we're going to write a couple more things here. And I'm going to write step one. So step one. So in step one, we have what we refer to as dynamic equilibrium, which is a term I've used before. We're looking at volatile substances. Next chapter, we're going to talk all about dynamic equilibrium, and we're going to talk about that for a while. Okay, so we have dynamic equilibrium. essentially by definition, when we have dynamic equilibrium, it means the rate of the forward reaction equals the rate of the reverse reaction. Rate of the forward reaction equals the rate of the reverse reaction. So we're going to use that to our advantage mathematically. Okay? And I'll show you how. Let's see. We're going to keep going on this slide. Okay, so if in step 1 we know that the rate of the forward reaction equals the rate of the reverse, we can write this in terms of our elementary reactions. Rate for that first step, forward direction, equals K1 times A squared, or A times A. If we look at the reverse reaction, now we have M decomposing into A plus A. Rate equals K, and I'm going to use -1 to represent the reverse reaction, times M. So all of this is coming from A plus A in equilibrium with M. And K1 is going to represent the rate constant in the forward direction, and K minus 1 is going to represent the rate constant in the reverse direction. So now we have two equations, and we can set them equal to each other because the rate of the forward reaction is equal to the rate of the reverse reaction, meaning these two numbers are the same. Okay? So we can do K1 times A squared equals K minus 1 times M. Oh, we're so close to the end of class. Okay. Now we have an equation, and we can rearrange this equation and solve for M. The reason we're going to do that, again, if we were to write the rate law based on the slow reaction, we would have to include M in there. But we can't do that. Okay? So if we have M, we're rearranging this. M is going to be equal to K1 over K minus 1 times A squared. I'm going to keep the rate constants together in a fraction. We have 2 more minutes. 2 more minutes. So what we're going to do now is plug this into the equation for the rate law for the slow step. Okay, so in our slow step we have B plus M forms C plus D. If we write the rate law, we'll have rate equals K, and I'm going to do K2 here for the second step, times the concentration of B times the concentration of M. And now we can plug M into this rate law. We'll have rate equals K2 times K1 over K minus 1 times the concentration of A squared times the concentration of B. Okay. So all of these K's, we're going to call one constant, and we're going to have rate equals K times A squared times B. And what we're going to see is that is the method for getting to the rate laws we have in fast